Strain energy is energy being when you an item or a structure you load the structure, the structure goes under deformation like a beam. So you put the structure load on it, whatever it is, uniform load or single load, the structure goes down. As soon as you remove the load, the structure goes back to its original position. That means while it was loaded or during the loading, there are going to be stored some energy into the system, because when you take all the weight of the beam back to the original location, that requires some work. And work is not free, of course. Everybody understands that it doesn't come free. So therefore, you load it, the energy is stored. That energy takes you back to the original location. So we are going to talk about that. So the first three problem is about energy. We call it strain energy, actually. So you want to add that to that one. I forgot to put it there in the other class. But this is due to the strain or due to the stress, doesn't matter, or due to the load. But we call it strain energy. So therefore, that's the subject we are going to talk about it. Then, of course, after we do that, you will ask yourself, what's the purpose of this? Why do we calculate strain energy in a system? Obviously, the next part of the homework will answer you that question, because through this strain energy which is stored in the system, please, we are going to calculate the deformation or displacement. Notice we used many methods to calculate the deformation. We used Hooke's law to calculate the deformation for an axial member, which was delta equal to PL over EA. Everybody remember that. We use many methods, singularity method, superposition method, this method, that method, to calculate the displacement under load in a beam, which was theta and y. Is that correct or not? We also, in ME 18-18, we calculated deformation, relative angular deformation of the shaft, one side with respect to other side, which we call it phi. Is that, you recall all of that? We are going to repeat all of that with the energy this time. So this is a new method. Of course, we are not going to use it for any problem. We usually use this method for type of problem. We cannot handle it with the old method, and some of them you will see it in your handout. For example, if you want to have the displacement of a truss member, which has lots of member in it, will be very difficult, because you cannot use geometry to calculate the displacement of node A or node B. Everybody understands. With this method, you can easily calculate the displacement of a truss, which we call it work and energy method. But unfortunately, that method has lots of limitation. So I'm giving you the idea of what we are going to do next in the next 2 hours or so. So then it has a limitation, and as we go through the limitation, we find out that that limitation does not let us to do many problems. It's only limited to certain problems with some certain restriction. Then we have to go through a theory, which we call it Castigliano theorem, which shows you how to use for every problem. Everybody understand that. So that theory will be discussed actually next Tuesday. So today we are going to concentrate on the 2-4 line. That's what I draw a line there, to understand what's the strain energy and how do we calculate that, and then to use it in order to find a displacement, which we call it work energy method. Is that understood? Yes or no? Okay, so let's go back again, categorize everything that we learned in ME 218 and 219 so far. I would like you to make a table in your note, because we are going to complete that table later. So here, put cases or loading, and then I can call it case 1, 2, 3, and 4. So I changed it. Here I put the loading system. Loading, you can understand what I'm saying, that we have gone through there. Then perhaps I want to put there, maybe next line, I want to put the stress. Then I want to put in the table a strain, probably, yes, a strain or deformation. deformation. Let's put the deformation. And then I want to put strain. And then here I want you to add, this is new now, energy or strain energy. I put here S, strain energy, and that has 2 columns. We are going to fill out that column today. Here is constant. Of course, you don't know what that means yet until I go through the whole system, and variable. And I define as we go there. So this is from this column on is today's lecture. This one, we already know that. Case 1, loading, we call it axial. So everybody knows what axial loading is, which was lecture 1, ME218. Yes or no? Any rod under pure tension or pure compression, or sigma equal to, in other words, sigma equal to plus minus N over A. I put N that you do not mistake it with the P. N was the internal versus the external. Is that correct or not? Then we had, of course, deformation for the rod. Deformation, I'm putting there because we needed to discuss it today. Deformation, delta was equal to what? Delta was equal to PL over AE or EA. Yes, correct. And the strain, of course, is normal strain, which is epsilon, that we are working in different format of. Epsilon is the amount of deformation per unit of length. Is that correct or not? Yes, that you are using there. And we get to the energy unit. Then, of course, as we go follow the ME218 system, from the axial, we went to the torsion, yes or no? But the torsion gave us the tau. So I'm going to put sigmas together and taus together. Everybody understand that? So the next item that gave us sigma was bending, yes or no? Okay, the bending give us a sigma equal to what? Sigma equal to plus minus what? My. I don't want to hear MC over I, because MC over I is a constant. It is on top and on the bottom. My means the stress in the cross-section changes, depends on the location of the point. Is that correct? That's what was some of your homework about. Yes, you used it in just the homework that I gave you. Of course, My over I. Is that correct or not? Which reminds you the stresses in the cross-section is not constant. It's variable. Is that correct or not? Then, of course, we had the deformation. What was the deformation of the beam? Of course, you should remember that one, because that was last week or a week ago discussion. What's the deformation of a beam? We spent 2.5 weeks on that one, guys. Theta and Y, yes or no? Yes? Why nobody answer me? All those calculations, the formation of this plate, we spent 2.5 weeks using singularity method, double integration method. You see, this is very interesting for me. Quite frankly, that's the way our students think. They just remember the procedure without knowing what this all about. We spent 3 weeks calculating theta and why. I asked from this class, the other class, what's the deformation in the beam? Everybody is quiet. What's the reason?
I was going to say because you were thinking of how to put it into a formula.
No, if that was your thinking, no. I said, what is the displacement? I didn't say, give me, because each theta is different. It depends what load you have. Is that all I asked you? What is the yeah, I'm sorry. If that was the case, then everybody knew. Is that correct or not? So let's put it this way. Okay. So that's theta and Y. And what was the strain? Of course, the strain is epsilon, because we basically, in many instances, we neglected the effect of transfer shear. Remember that? So we said that's minimal compared to the other one. Anyhow, so that was epsilon. It could have gamma, but I didn't put it there. Then these two are sigma, and these two are tau. Remember how you were calculating tau? Tau equal to Tc over J plus minus Eq over T. I'm just referring to that. So we had the torsion, yes or no? Yes? So the torsion, what was the stress? Stress tau equal to plus minus, because you know that, T what? Not Y here. Just this one had Y, this doesn't have Y. That's exactly again here. T what? TC over J? Wrong. Okay, it's a variable. It is not a constant. TC over J is outside. What was C? Actually, C was when outside. Rho 0 is inside. Rho C equal outside. It was a circular. Remember, we have to go through. Okay. So you remember it now. Okay. T rho. Exactly, if you are calculating a stress here inside the shaft, the stress is like that. Is that correct? Remember, we went from rho, and rho was between 0 to C. Those was the derivation of equation. Nevertheless, these are, I'm talking about not outside only. You are using outside, you know why? Because as a designer, you're interested to find the highest value, but in general, that's the format of a stress. Is that correct or not? In the beam, top with compression, bottom with tension, it has a parabola format or linear format that we all have gone through ME280. Anyway, I don't have to mention that. And what was the deformation? Phi, that's correct. Phi equal to TL over GJ. Of course, you had plus minus because it goes clockwise, counterclockwise, etc., etc. Obviously, because this is the shear stress, you will have the shear strain, which is gamma. And as I said, there is case 4, which is transverse shear, which that was chapter 6. The tau equal to plus minus VQ over IT. But for this system, although there was a gamma there, et cetera, we never calculate that one. But we are going to bypass that, or we are going to assume they are negligible. So please write it down. Actually, they are not, but it has a little bit more difficult. So we are not going through that, because with the type of problem you have, which is really very long and narrow shaft or a beam, the effect of transverse shear generally is negligible. I don't know whether you notice it in some of your problem. TC over J was always 20 times larger than VQ over IT, unless you have a short column, which does not qualify, a short load. Is that correct or not? So let's leave it at that. Anyhow, this one we are not going to cover, let's put it this way, but it is there. So we are going to go through this done, and now we want to fill out this. Now, to do that, we start with the axial member. So I'm going to put an axial member here, as I did for other class. Then I'm going to put here a load here. Let's do it a little bit larger. These are in exaggeration. So I put here a load P1, and I will get delta 1. Everybody knows that. And then I'm going to plot here P versus delta in general. This is not Hooke's law, because in Hooke's law, remember, we were plotting epsilon versus sigma. Here is load versus deformation. So that's a different thing. However, the same principle applied. Everybody understand that when P1 equal to 0, delta 1 equal to 0. So we started here. And then as we increase the P1, delta is going to increase. But if we are below the sigma yield, everything is linear. Yes or no? Correct? So we linearly going up like that. Is that correct or not? Let's say at this scenario, this is our P1, and this is our delta 1. Is that correct? Whatever it is, well, we can plot it so we can. Then at this point, suddenly we are going to add to our P1. Let's say the P1 is 10,000 pounds, and we have a rod here with the length and cross section. We put the load here. Notice, as soon as I load this, there is an energy being stored in the system, because it is a stress and it's a strain. We don't know yet how much it is. We are going to find out in a minute. However, if I add to this load another delta P, so let's say with 10,000 pounds suddenly become 10,010 pounds, so delta P is 10 pounds. Obviously, the deformation will increase a little bit as well, yes or no? So we are going down a little bit. Oh, this is much smaller than the other one, of course. We are now at this level. That means I have added to my load here, and of course, my delta increased. So I'm going to call that delta delta. So this one is delta delta. A little bit more, whatever, although these are all small number, but that's the scenario. Is that correct or not? Yes? And we are there. This is added a little p here, added a little delta there. Is that correct or not? Now, at this, in order for you to understand what is going on, at this time, suddenly, you should do the same thing. Remove the delta p. Yes or no? Yes? Correct? Notice P1 is hanging here. It's going to be moved up. We are going from the purple to the black. Is it the work being done here? Of course, that is the energy that was stored, because if I didn't have energy, it would not go up again. Everybody understand that. If this was a plastic material, probably that would be the case. It stretches, never goes back again. Is that correct? This is elastic material. So I need some energy which was stored here to take. How much is that energy? Write it down. How much that? We call it delta U. So we show the energy by capital U. So all of this will be U. So I'm putting here a straight energy U, or capital U, which shows the total energy stored in the system. In this case, I have a little bit energy stored here, which is what? P1 times, look, P1 is here. From here goes to here. That's the amount of work. Work equal to force times distance. So it is P1 times what? What's this? Delta. So delta U was equal to, because of that adding delta P and removing it, I have stored this much energy. Delta P times delta, how much delta? Is that correct or not? Yes? Correct? P1 times delta. P1 times delta. Can you show me area-wise what is that number? Is this P1? Is this delta theta? Yes or no? So that U is this area. Yes or no? Yes? So that area that you see there, that band, represent the total energy that I stored in this system when I went from P1 to P1 plus delta P. Yes or no? Therefore, if suddenly I change the whole thing, and suddenly I put here the general load, because this goes up linearly until we get to the elastic range, because we always load the structure before we get to the sigma yield. Is that correct or not? So if I go to any P now, so let's put that any P, which I put blue. So if I load this structure to point P and delta, this is point P, and that is delta, what's the total energy? Isn't that the total energy I have stored in that? Because I have to add all those little strips together, yes or no? Because this is 1, but notice they are not constant. Actually, they are variable. So you go this one, that one, that one, that one, that one, all this little strip added together. So the total, which is the total U for entire system, if this structure is loaded to the load P, which is there, and delta there, will become this area, the blue area, yes or no? Which is equal to what? Equal to P times delta divided by 2, because it is a triangle. So will be 1/2 of, that's what you want to know, P times delta. So that is the total energy stored in a axial member. However, what's the value of delta? We already know what the value of delta is. Is that correct or not? What's the value of delta for axial member? Delta equal to PL over EA, or AE, as you say. I always say EA, you say AE, that's all right, both of them the same. So total energy U, of course, remember this equation, because we are use that for the work of energy. But total, if I substitute delta in that one, it becomes P square L about divided by 2 EA. Because this becomes PL over EA, 2 is there, another P. So it's become P square divided by 2 EA. So I'm going to put that one here. Energy equal to total energy. I don't need to write it here because I already wrote it there, but nevertheless, equal to P square L over that. L. When everything is constant, that means the area should be constant, the load be constant, because this is the length, is area, etc., etc. Is that correct or not? Then we get into a little bit of problem if we progress to the beam. Look what happened in this system, guys. In this system, sigma here and here and here and here and here is all the same. Yes or no? Agreed? Epsilon here is all the same. Is that correct? So everything is constant. So every part of this structure or this rod contribute the same amount to the energy. Yes or no? Now, if I change this problem to the second system, this is what I cannot use this equation for second system unless I modify that a little bit. If I use a beam now, which you used it in your homework, a couple of beam, I noticed some of you were even asking questions before the class start. Yes or no? Remember the beam I gave you with strain gauges, etc., etc.? If I give you a beam like that, and I put here at the end a load, which was one of your handout problem, yes or no? Do you think every part of this structure contribute evenly, like here? No. Actually, it's totally different. Here, if I color code it, let's say all of this become dark red. Is that because all of them are participating the same amount, except, of course, stress concentration, we are neglecting that. Everybody understand that, yes? Here, as everybody appreciate that, you have done all your homework, you know that not even stresses changes this way, stresses changes that way as well. Is that correct or not? So where do you think this one will get, if I color it and red is the highest energy, where I'd get the maximum redness, for example? At the end and on the top and on the bottom, because on the neutral axis, the stress is 0, the strain is 0. Everybody understand what I'm saying? That therefore, the distribution of a strain or a strain energy is not uniform because it depends on the sigma or it depends on the strain. Is that correct or not? Depends on the stress or a strain. So based on that, we are going to, everybody understand why I'm doing here. The difference here is everything is constant. In other words, if I'm saying that if I use 1 cubic inch of material here and 1 cubic inch of material here, both of them give me the same amount of energy because they have the same sigma, they have the same epsilon. Is that understood? Because if you don't understand that, I cannot go to the next phase of the operation. So based on that, I'm going to define a strain energy density. Please write it down. So a strain energy density is this, which we call it small u, and I put typically a E in front of that you see. And that is, write it down, that's the meaning of that. The strain energy density is the amount of, first of all, it's energy density.
Is this still for axial living?
What?
Is this still for axial living? Or just for everything?
It's for everything. But that's the definition. This is the definition. It has nothing to do with that or the other one. I use it for that one, then I expand it. Yes, but this is for every problem. Doesn't make any difference. Energy density. See, all I'm saying that energy density in this rod is constant. Energy density in the beam is not constant. Somewhere is 0, somewhere is the highest value. But I have to calculate total energy. So as you see, I have to use integration. Everybody understand what I'm saying there? Because it's not constant. Therefore, I'm defining energy density, which is what? See, I want you to understand that. It's very important for the other class. I explained that. What's the difference between delta and epsilon? Everybody should know that by this time because you've used 10. But if you pay attention to what's the delta? Delta, any delta. Delta is total axial movement or deformation. Yes or no? What's the epsilon? The amount of deformation per unit of length. So that is the unit. Is that here is this is total energy. Now I'm calling energy density, which is similar to this is, write it down. Energy density is, this is the definition of that, amount of energy stored in 1 unit of volume. Because it's not epsilon, this is energy. Energy depends on the volume, yes or no? I cannot have a flat plate and have energy. I must have a volume. Yes? Correct? So that is the unit again. Remember, this we are going all the time like that. P is total load. Sigma is the amount of force per unit of area. In a way, it's unit. Delta is total deformation. Epsilon is the amount of deformation per, because this is the system we are using. That's why sometimes you have integration, sometimes you don't know, sometimes they are constant, sometimes they are not. But this is typically when you get in the higher class courses or more mathematical, that's how you have to think about everything. Is that correct? Actually, it's become much more complex than that later on mathematically. Now we are defining total U and unit density, energy density, which is the amount of energy stored only in one unit. It could be millimeter by millimeter by millimeter or inch by inch by inch. Everybody understand that? Yes? Which some of us are go to sleep because we don't want even to listen to that. So you have to write that right there. Amount of energy is stored in what? Unit of volume. This is the key for entire understanding of the rest of the problem. So if you write that, what will be our energy density for this rod? Notice it's true that all of them are participating. What's the total energy? This is the total energy. Because everything is constant, can I divide that by the volume and find out the energy density? Yes or no? So let's do that. For the rod, that's what you asked me, but it's applied to anything with the sigma. So for energy density, since it is the amount of energy per unit of volume, I put the total energy and divide that by my volume. Is that correct or not? Yes, so therefore I have P squared L divided by 2EA divided by volume. The volume of this rod, of course, I don't have to go thickness, etc. We go L and the cross section A, because we never defined the cross section A. Is that correct? A is area, could be square, could be, etc. So will be divided by what? What's the volume? Volume is LA, not LA, right? Not LA or LA. It is length times area. Is that correct or not? Yes? Correct. So therefore, as you see, L and L drops out. You get P squared over A squared. So it becomes equal to P squared over A squared. So it becomes sigma squared divided by 2E. So as you see, it's related to sigma. You said sigma is, you see now you understand it. Sigma is constant. Therefore, energy is constant everywhere. Is that correct? For the beam, sigma is not constant, energy cannot. Sigma is zero, energy zero. Is that correct or not? Yes? Correct. Therefore, so that's it. So this, you want to put that equation also in the system. I'm going to keep that here. Energy density equal to also, doesn't matter now the first problem or second problem. This is based on sigma, not PL, etc. So it is sigma squared divided by 2E. However, since we know from the Hooke's law that epsilon equal to sigma over E, or sigma equal to E over epsilon, I can put E squared, epsilon squared there, eliminate what of that one, and that one become equal to like that, or become equal to E times epsilon squared divided by 2. Either of them is acceptable, but we use the first top one because that's the one we have.
Wait.
That's, as you see, I can use the stress or I can use the strain. That's why we call it the strain energy. Anytime you load the structure goes through sigma, yes or no? The structure goes through epsilon, therefore it's going to store energy in it. You let it go, that energy do the work, and we want to calculate that energy. These are the primary formula you want to have that. Of course, these two are only for rods, but this two is in general. Is that correct or not? That's what I want to we use that for the general purpose. Now, look what will happen. If I do that, and those are my formula, I'm going down to do a series of problems that we could not handle previously. Obviously, it is so silly to use this method for a rod because we already, week 1 of ME 218, we explored the rod in detail. Yes or no? Who wants to use energy method for the rod? You know when you want to use that method? That's the reason. You are using this method if I give you this problem. If I give you this problem like that, and I put here a P, can you solve it? See that? What is sigma constant here? No, because area changes. Yes or no? Let's assume the thickness is constant. Assuming, write it down. If the thickness is constant, the area keep changing. Yes or no?
Therefore, sigma here, sigma there, sigma there, sigma. So I cannot use that constant. Things become variable, especially area. Yes or no? However, I can use this technique now. So this is the technique you are going to use. Total energy. So you want to write always equal to energy density, because energy density is how much? Is the amount of energy stored in a unit volume times dV, has to be integrated over the entire volume. So that would be our general equation. In general, no matter what I have to go through the integration, which is x, y, and z. Yes or no? But in many cases we avoid that. Of course, like as usual, we don't go x, y, z because some of the problems are constant. Look at this problem. Is sigma in the y direction is variable if I go to this line? Is sigma here in this direction variable or the same?
In which direction?
Same. If this way is the same, this way is the same. In other words, if I look at this has a thickness here. Is that correct? If I look at this way and this way is rest are constant, yes or no? So only I have to integrate it over x. Although the general equation is volume over the volume, but I don't need to integrate that over the thing. You will see what I do in a minute. So this is my problem, yes or no? So a is a variable, a is a function of x, so a keep changing. That depends what parabola you have here or what line you have here. I will give you in. I'm saying that for our type of problem, E always is constant, yes or no? Because modulus of could be variable, but the P could be variable. In this case, A is variable. Also for the other class, I mentioned the problem that P is variable, that we have never mentioned, but we should have mentioned it. But we avoid all the mathematical problems, right? If I have a rod here with this, and it is, let's say, 10 foot long, and it has a cross section, and let's say each foot of this is made of material which has about 50 pounds per foot, then what P do I have there? Is it going to be stretched because of its weight?
Yes.
So how do I represent them? Is the weight constant?
It's 10 times.
I mean, you don't put the weight at the middle here. Is that correct? If I'm here, how much weight do I have? This much. If I'm here, how much weight do I have? Everybody see what I'm talking about? The weight or the force acting in this member as P is a variable depending where I am. Is that correct or not? That problem by itself requires integration. Everybody understand what I'm, even for delta, calculating the delta. Because P is not constant. So we are really, when we say P is at the end, we are simplifying lots of equations. So get ready for graduate work, which you are not going to do this type of work, because everything has a real scenario versus the one that we are assuming. Where is concentrated load? We all change everything to a concentrated load at the middle. Yes or no? Correct? So that's not the truth. So anyhow, so what I'm saying that even this simple problem requires integration. What I'm saying that anytime that this tree, so I put here integration, U equal to this capital total energy. And that's equal to 0 to L P squared divided by dx. Of course, notice if A is constant, right now you have to put A as a function of x. Everybody understand that when you come 2.5 x to the power of 1/2 or 2 or whatever, depends on those lines, you have to do a difficult integration as well. Everybody understand? However, we are not going to go. But if A is constant, E is constant, P is constant, everything comes out. Yes or no? Yes, and then become integral of dx. What's integral of dx? Is x to be evaluated between 0 to L, so it becomes P squared L divided by 2EA. Everybody understand, which becomes this one. Is that correct? So this is constant of that one. Everybody see that? Because integral of dx is L. But if any other item like P or like A was a variable, I have to put it in that equation and I have to use the index. This is one example of this, that, which we are going to do it for torsion as well, because you are going as a mechanical engineer, you are going to design item. One of the items that I like very much, you can put a, this type of item, is just like that, and put an axial load or torsion and that sort. But this is the method to use. Is that correct or not? Also, remember that when we go to the higher classes, like the design classes, machine design especially, I've noticed that many times Dr. Anderson gives you lots of problems that you have to solve deformation-wise because part of your machine design, which is not the standard beam and column. Everybody understands. So this method comes handy. You have to remember this. Is that correct or not? We'll see when we go through the example. We can do lots of things with this method for particle. We use it for this to explain to you what's happening. Everybody understands it. Then we expand it into more difficult problem. Now let's go to problem number 2, which is the bending. Is that correct or not? Let's see whether we can find out the equation for bending and the torsion, and then we'll see what happened afterward. These are now, if I want to calculate strain energy in the rod, either I use this one and that one. Which one is more common? The one more common one, I put it in the box. The more common one, of course, will be this one because you have it all constant. So let's say you have a problem here, like this. I'll explain that at the end. Let's go now to bending. Now let's go to bending. This one is a little bit different, but it's the same idea. So this is bending. I just put one load here, P, doesn't matter. So that's the symbol. Doesn't matter how many loads you have here. But in this section, when again you are at X and delta X, the sigma changes, yes or no? But this time I cannot take a vertical volume only because on the Y direction the stress changes as well, yes or no? That's why I wanted you to say Y. Everybody understand that. If Y equal to 0, you are on the Y equal to 0, you are on the neutral axis. You go up, for example, you are either tension or compression, depending what kind of moment you have. Is that correct or not? So one side is tension, one side is compression, and the change is linear. We know that from NE to AT, correct? Therefore, I cannot take the volume. However, I know in the depth of the beam, the stress is constant. So that gives me only two integration, X and Y, not Z. Everybody has, because Z, the thickness is the same, and the stresses in this direction always were constant. We recall that when we were doing this. So here was all compression, here was all tension, or vice versa. So Z does not come into the picture. Is that correct? So for that reason, I can choose by element the same way as before. So let's say if this has a cross section like that. So if this is the neutral axis, and we are here, and we call this one dA. Is that correct? And this distance is Y. Is that correct or not? So I can choose by dA a strip like that, which gives me, again, this is neutral surface, and this is my element down. My element down is something like that. Yes or no? What is this dimension? dx. What is this dimension? dA, because this could be any shape. Everybody, I'm just putting it here. So my volume will be like that, but my unit volume will be what? My PV will be what? Will be dA times dx. dA times dx. So that means I have to integrate over x and integrate over y. Is that correct? Yes? Because quite frankly, maybe I should not draw that, because I can draw like that. Everybody see what I'm talking about. This dA keep changing too. Is that correct? It could be round, it could be circle. It's always not like that. This one doesn't make sense, but that's the general rule. Is that correct or not? Yes? So therefore, that's what it does. Then we get to the formula again. Total energy, write it down, equal to what? Equal to over the volume, which is x, now y dot xd. So the energy density. What's the energy density? Energy density, I erase it, I'm sorry, was sigma squared divided by 2e. Is that correct or not? So let's write it down again one more time. Sigma squared divided by 2e times be, which in this case become equal to integral of sigma. Sigma is m squared, yes or no? Yes? Y squared over I squared, correct? My over I. But doesn't matter whether plus or minus, because we have plus minus. When I square it, become m squared, y squared, I squared. Is that correct or not? Yes? Divided by 2e, that is this one. Yes or no? Multiplied by my little volume. What's my little volume? dA and dx. dA times dx. Now everybody knows from the previous discussion that we had that m is not a function of y, m is a function of x. Is that correct or not? I is a constant, yes or no? E is a constant, but y is a variable and dA is a variable. Is that correct or not? So this formula can be written like this. Integral of m squared divided by I squared times 2e, which is there, I squared times 2e or 2i squared, and then y squared dA integrated over the area. This is one formula. Y squared dA, because I have to go over the volume is x and a, and this one will be 0 to L, so for the x part. This will be this, and then we have dx here left it there. So this dx, y squared dA, because this is over the volume, I separate that area and the length. So what is y squared dA, guys? What is integral of y squared dA? Moment of second moment of inertia or second moment, yes, or that's I. Is that correct or not? So y squared dA become again equal to I, but that's the definition of the I. Is that correct or not?
Yeah.
I lost you?
Yeah.
Not, I hope not, because I have mentioned it many times. Y squared dA is moment of inertia. One more time, guys. It doesn't hurt that to bring everything together, because if you are missing, some of you, not all of you. So if this is dA, I mentioned that in this class 2-3 times. dA times y is what? dA times y is q, yes or no? dA times y squared is moment of inertia with respect to this axis, horizontal axis. And if this belongs to the larger area, all you have to do, write dA y squared and integrate that over the entire area. That becomes the definition of moment of inertia. All you need for chapter, I don't know, 2 chapters in the static, centroid and moment of inertia. dAy is qx, dAx is qy, dAy prime is ix, dAx prime is iy, and dA rho square is polar moment of inertia. That's it. That's the entire 2 chapters that you are looking for, but it is that simple to go based on the idea. The rest is formulation. Is that correct or not? You have to use that integration to come to moment of inertia for a rectangular shape, which will end up to be 1/12 of base time I cubic. So that is the principle. Nevertheless, look what happened. This I and one of this I drops out, and finally this becomes integral of 0 to L m squared divided by 2ei dx, which is very similar to the other one. So therefore u here become equal to, put it into total energy u become integral of 0 to L m squared. Look, this is repeated, but instead of 2e is 2ei. Everybody understands? And some of you may think that this is very difficult to remember, but actually it is very easy to remember. I give you the key. I gave it to the other class as well. Look at the key. Everybody remembers PL over EA? Yes or no? So all you have to do, make the load, remember this, make the load square and then put a 2 here. In other words, add a 2 there and put a 2 here. Everybody see what I'm talking about? Look how routine that. PL square L divided by 2EA. Of course, EA belongs to the axial load. EI belongs to the beam. Anytime we were calculating theta and y, we were using EI. Yes or no? Correct? Okay. Now, if F, now this is M. Is this, in this problem, M is constant or M is variable? Variable. So you have to write M as a function of X all the time. So this is more common. See, this is more common for us, and this is also more common. So M, you remember how many times in the previous chapter we write M as a function of X? Here you have to do the same thing. You have to be able to write M as a function of X. Of course, we simplify that a little bit. We'll see that later. But however, could it be M constant?
Yes. Yeah.
Yes, of course, everybody knows that. Where is the component? Give me an example of M constant.
If it was just a moment on the other. Yeah.
Absolutely. Is this what you are saying? Is that correct? Is that M constant? You see here, M, you have seen it in the past. So if it becomes constant, that's what the other one is. So U become what? See exactly the same format. U become equal to what? M square or MO square, because now we call it MO. The reason is that you know what? See, when you put MO, it is constant. When it is M, it is usually a function of X. This is what we do all the time. W is function of X. When you do WO, it is a constant. I don't know if you notice in all your problem or not. You never notice this sort of thing. That's the case. All right, welcome to the class. So therefore, MO square L divided by what? 2 ER. Is that correct or not? Yes? Okay. Now, there are similar formulation for the torque. I have to do the same thing. I do that, I do that. There are, this time, instead of sigma versus force versus delta, I have to write phi versus T, but the same thing applies. You don't have to do that. Can you give me the answer for this? By looking at what happened here. Can you give me the answer for
T
this?
squared L squared.
Of course, yes. U equal to, as I said, this is typical. T squared L divided by what? 2 what? 2, what's the? G. Modulus of, and J. Is that correct? Because that's the formula changes. Is that correct or not? Yes? So I don't have to drive that for you. So you can see it by similarity. But is this, now for integration, if they are variable, what should I do? T squared divided by 2gj dx. Now remember, T could be a variable, J could be a variable. As I said, G could be, what we never use it in this class, of course, or undergraduate work. Is that correct or not? So we are assuming G always is constant, which is modulus of rigidity in every direction. Everybody understand that? And then, therefore, J could be, because I can give you a conic shaped item and I put it under the torsion. You can design something like that. Yes or no? Then you can calculate the phi for this method. This is for a special problem. Everybody understand that. However, we use it for regular problem as well for you to get used to it. Is that correct? So if I give you a regular beam or regular shaft to calculate all of this, it's just for the purpose of learning. But in real life scenario, we use it when things become a little bit more odd shape. Is that correct or not? So I want you to know why we put this for last. Anything a straight line, we can use one of the other methods. Lots of solution were in the back of the book. Yes? Okay, so that's it. Now. And that's it. So we are not using there, so that's the system. Now, you have to say, what is this for? So I give you now a series of examples, because I don't have time to go through the whole thing, but I want you to, over the weekend, to really look at all these problems and try to do it, because I'm going to do a couple of them, but you should be able to, but I'm more interested in this one, because you know what this one is? It is like knowing the moment of inertia of the rectangular is 1/12 of base time height cubic, and you don't know parallel axis theory. Is this useful to you? No, it's very limited use. Without parallel axis theory, this is very limited use. When I explain to you what the work of energy is, you will find out that there is lots of limitation here, and this Castigliano theory makes it more general. Everybody understands. Now, here is the problem. If I give you this problem, which is the simplest problem I can think of. Can you calculate total energy there? Yes. But you have to do it in 2 parts, yes or no, like before, because everything is constant from A to B and then from B to C. So you use this formula, depend what L I give you, what E I give you, what P I give you. You can calculate total energy stored in this beam, yes or no? Or if I give you this, the same problem, but these are circular shape, and I put here a torque, then you can calculate total energy using this function. Is that correct? And if I give you this beam, I'm putting all of them, and a load here P, let's say P is given, this is, let's say, A, and this is B, A and B, but P will be given. Again, I can find the total energy stored in this beam. However, in this beam, I have to use the integration, because M is a function of X. Everybody else. For this one, I have to use constant added together. Constant added together. This one, I have to use from A to B, separate from B to C. I'll show you the technique next time, but I want you to get into this habit. Hopefully, you will do some of this by yourself. If you get into difficulty, I'll tell you how this works. Is that correct or not? Yes? And then you will ask, okay, what's all of this good for? So, okay, I find that this total energy is not that much pound-inch of energy. So what? Yes? So what is work and energy method? So all of them, we are, oh, I forgot one more thing, the most important. Let's say that I have here a truss. Remember, this is a truss. So, how should I put it? Oh, I make it the same way for the other truss. Let's say this is the truss, the 5-member truss. Let's say here is a pin and here is a roller. Yes or no? Correct? And I put here a pin. How do I solve this problem? Which one is this one? Is it case 1, case 2, or case 3? That's what I'm asking. Case 1.
Those are all pins, right?
All pin. I said truss. When I say
Okay.
truss, it is all pin. Yes or no? I said this is not a frame. I said this is a truss structure. Truss means all the member are 2-4 member. Actually, some of your problem are like that. I have a couple of problems like that too. I'll show you that. So in this case, you have 1, 2, 3, 4, and 5 members. Let's say if I give a P, for example, equal to 5,000 pounds, you have to find force in each member. Doesn't matter whether they are tension or are because it's square. Remember that. Because both of them, both tension member and compression member, contribute to the energy. Yes or no? Doesn't matter whether they are plus or minus. Okay, I calculate force in this member A, B. So this is A, B, C, E, B, D, 5 member. I have to add all of them together. Is that correct? So what? Okay, I find the energy. I haven't done anything yet. Everybody understands. To come to the work and energy. The work and energy, the equation that I have written down earlier, you have to look at that one. It was for the axial member, total energy was equal to 1/2 of P times delta. Yes or no? So if I calculate the energy somehow with that method, then I can that make it equal to 1/2 of P times delta. So I can calculate the delta. So if I calculate total energy of this structure, I can calculate some delta there. But then I have to tell you what the work and energy idea is. It is some theory that I'm not going to go through that, but I give you the end result. So please write it down. All of this total energy you find here, or find here, one here, is sums up into this idea. Look at this idea there. So I'm going to put it in general format, but I'm going to explain it to you. The numerical example will come next time, everybody, because I don't have time and I want you to do it. So every time you calculate U in any system, doesn't matter. This system, doesn't matter which system there is, always U equal to 1/2, but that 1/2 comes from triangle, yes or no? Times the load, whatever load you have. Now, load, you change it. If it is the torque, you put T here. If it is M, you put M here, P there, whatever you have. Notice the loading can change. Everybody understand what kind of load you have there. Then times what? What was at the end? At the end was displacement, yes or no? But that displacement, you have to qualify that. Times displacement. But this is through the theory, this can be proven. I'm bypassing it. But that displacement is in the direction, I put this in capital, in the direction of load, but under the load, yes, under the load, but that's the same meaning, in direction of the load and corresponding to the load, in the direction of the load and corresponding to the load. Now, let's see what happens here. Okay, that's why it has a limitation. Now, if I'm calculating total energy here for this member, this point C moves this much forward, yes or no? So therefore, what I'm calculating is here is delta. Everybody understand? Delta must be in the direction of the P. Is that correct? Because it's a direction. And corresponding to P is delta, because that is appropriate deformation for axial member. Everybody understand that? So then if somebody comes and asks me, what is the formation here, everybody understands that because beam goes forward too, yes or no? Can I answer that question? No, not at all. Until we go through the Castigliano method, because this is, write it down, this method, because this is only one load, not two loads. I cannot have two loads. If I have a load here and load here, I cannot write that because I have only one load and one displacement, yes or no? Please write it down. So this is limited to one load, this is very important, and one displacement only, and that displacement has to be corresponding. Has to be similarity with the load. So if you are talking about P or N, you are talking about delta, yes or no? If this point goes up and down, I cannot calculate that. Everybody understand that? We come to here, all I'm calculating phi at C. I cannot calculate phi at B. When it comes here, now what am I calculating? If you answer me that question, then we go to the quiz. If I calculate that, what will I do that? This beam is going to bend like that. Is that correct or not? In the direction of the load, yes or no? Will be Y. Actually, somebody come and tell me theta, I cannot do it. Is that correct or not? However, if I have a beam like this, let's change that. Put that one in your note too. If I have a beam like that and there is an MO is involved here, and this beam bends like that, for example, which is not true, is that correct or not? What am I calculating here? Not Y. Select corresponding to the load. What's corresponding to the load? Under this, what am I supposed to measure? Angular deformation, not phi, theta. Is that correct or not? So please write it down in your note. This is something you're still not getting it. Look guys, there is an R and there is an M there. Yes, R is for what? R is for Y, M is for theta. These are corresponding. So that's why some of you do not consider the M. If you don't consider M, you don't consider the theta there. Everybody understand what we have gone through that 10 times. So corresponding to this load is Y. Corresponding to that load is theta. Everybody understand that? So if somebody wants theta here, I cannot do it. If somebody comes Y here, I cannot do it. Is that correct? So there is a way around it. We'll see that next time. Is that correct or not? However, that's what we are going to do. One load, one displacement, that's the form. The other problem is this. If there is AB here and there is another load P2 here, which displacement? I cannot tell. Is that correct or not? So this is limited to one load and one displacement in that scenario. So you go there, we calculate that. So you should be able all to calculate, do all your homework in the first two lines until I get to the Castigliano. By the way, I'm going to do some example, but I would like you to start with it. Is that correct or not? Yes? So it should not be that difficult because these are all routine. Most of them, by the way, this one also, this is the most common. So actually this one and this one you go do the integration. This one you do the integration also. The most common. Okay guys, so let's go to the quiz.